Hello everyone, this is Dr. Hopkins with our next in our series of videos where we're considering redox reactions in this case, and we're going to continue in terms of electrochemistry. So we had this, we left off the last video, with the idea of the cell potential telling us whether a redox reaction is spontaneous or non-spontaneous, whether it's positive or negative. And so we have this idea of spontaneity, which has to be related to delta G because we know delta G dictates spontaneity. And so we have a mathematical expression where the delta G is equal to minus NF, the E cell. N is the number of moles associated with of electrons in the redox reaction. F is the Faraday constant, which is basically the charge of a mole of electrons. And the E cell potential is our cathode minus anode that we figured out from our particular half reactions. So if we consider what we were doing last slide, we had the zinc and copper, zinc in the anode, copper in the cathode. We had these two half reactions, and you recall the E cell potential for that was plus 1.1 volts. You'll notice that each one of them loses or gains two electrons, so our N in this case would be 2. So then we would plug in these values for into the equation we had in the last slide, and it's 2 times 96,485 times 1.1 volts, and we end up with negative 212 kilojoules, which is definitely less than 0 and shows that this reaction, this galvanic cell reaction, is spontaneous, which matches with our E cell prediction, which is it's spontaneous. Now remember, if we have a delta G, we can calculate a K, which also tells us whether something fits to products or reactants. And so if we rearrange, delta G is equal to minus RT natural log of K, so K is the exponential. There's a negative sign in front of that fraction. It's hard to see. And that ends up, we have 212,000 over 8.314 as our R. 298, we're going to assume room temperature. And that gives us an extremely large equilibrium constant of 1.45 times 10 to the 37. So why don't we try a different galvanic cell? Let's look at silver being reduced into silver and then copper being oxidized into copper 2+. So if we look at the reduction potential, so we have our cathode, which is going to be our silver, minus our anode, which would be our copper, and then we're going to calculate the E cell potential, the delta G, and the K for this reaction. Here we have the problem set up. I've got the overall reaction written. I have the reduction potentials of the two half reactions, and I've identified the silver as our cathode and the copper as our anode. So what we want to do is determine our cell potential, the standard cell potential in this case, cathode minus anode. So we would plug in our cathode, 0.80 volts minus 0.34 volts. And if we subtract those, we're left with positive 0.46 volts. Okay, so that should be spontaneous. So let's determine the delta G. It's minus NF E cell. Okay, so how many electrons are we what's the number of moles of electrons in this case? Well, you'll notice we have 2 silver and 1 copper, but the copper is 2 electrons, so we still have 2 moles, just like the example previously. And then the Faraday constant is 96,485, and then this is 0.46. If we add those together, we end up with negative 88,000, essentially 800 joules, or it's negative 88.8 kilojoules. So once again, a very large spontaneous number. So let's figure out K. Okay, we're going to start with delta G is equal to minus RT natural log of K. And then that means that K is equal to e to the minus delta G over RT. So it would be 88,800 over 8.314. And actually, I didn't specify a temperature, did I? But we're going to go ahead and do it at 298 Kelvin because that's important. This is E. And so this K is 3.63 times 10 to the 15th. Okay, at 298 Kelvin. So once again, large favors products, much like what our delta G and our E cell are telling us. So the last problem we did was under standard conditions. We have that E cell not. And the standard conditions are defined as all solutes are 1 molar. So what if we have solutions, or our aqueous parts of our galvanic cell are actually less or greater than 1 molar? How can we factor that in? Well, we have this idea of free energy is equal to the standard free energy plus RT, natural log of the reaction quotient. So if we're not at equilibrium, we have a reaction quotient. It's moving towards that delta G naught. And so we can then substitute in, we do a little bit of math on that minus NF E naught. And so then the E cell, the cell potential, is the standard cell potential minus RT over NF, where N is the number of moles, F is the Faraday constant, R is our gas constant, T is our temperature, and then natural log of the products raised to their stoichiometric coefficient over the reactants raised to their stoichiometric coefficient. In that case, that equation is called the Nernst equation. So we're going to go back to our original zinc and copper galvanic cell. And let's see what would happen if we put zinc as 1.1 molar and copper as 0.9 molar. Let's solve for the non-standard E cell. So here we have the problem set up where we're going to write it out. We have our reaction, zinc plus copper 2 plus gives us zinc 2 plus plus copper. We have our standard cell potential, which we solved in the last video, of 1.1 volts. Okay, so it's a spontaneous reaction. And that's in our standard conditions where zinc and copper, the zinc and copper 2 plus are 1 molar. So what we're going to do is, what would happen if this reaction moved along and it generated 1.1 molar of zinc and 0.9 molar of copper. So let's say we've been running this battery for a while and we've dropped the concentration of the reactants, increased the concentration of the products. What's our cell potential? So we'll solve this, We'll solve this problem. Here we have our standard cell potential, which is 1.10 minus, and this is 8.314. Once again, I didn't specify a temperature, but we're going to use 298 divided by 2, because remember that was a 2 electron redox process, and this is 96,485, and then this is the natural log of 1.10, over 0.90. All right, because we substitute in our concentrations here and here, and we're left with that. And so this would be 1.10 minus, if I do this, what is it, 0.012 times 0.206, and I get something like 1.097 volts. So to 3 significant digits, so if we were to go, so you can see you have very little change, which is actually very important. If we had a battery, if the cell potential of the battery dropped rapidly, when you have a 10% of the battery converted, then that wouldn't be any good. It wouldn't power your electronics. So the fact that it maintains its cell potential, its voltage, because the standard voltage dictates most of it is very good. So if we were to, let's just take an example where we had the concentration of zinc and we let it run to 1.75 and copper was at 0.25. So let's say it's run 75% down. We're at 25% power. If we did the same math, same process, our E cell in that case is 1.075 volts. So still not far away. So it's still plus from our 1.10 volts, which is really important that a change in concentration doesn't change our cell potential very much. And last but not least, we have the key takeaways from this video. The cell potential and delta G specify our spontaneity. If we've got delta G, we can figure out the K. Typically in these redox reactions, if they're spontaneous, these galvanic cells, they're really spontaneous. In other words, the Ks are just very large. We wouldn't even need to write equilibrium. Standard state, of course, to remind you, is condition where all solutes are 1 molar. So if we have non-standard state, we use the Nernst equation to figure out cell potentials. So until next time.